those things?
Yeah, somewhat. That's how I first rodeo.
Shall we get the barbell back over?
Thank you.
Oh, Ashley. Okay, so it's time to start. Welcome. So I want to review a few things and then we will review for exam 3 that's on Tuesday. As you can see with the course outline, where we're going, we have a review activity today, and you do have that epidemiology assignment. So before I forget, why don't I just go around and collect that if you haven't already sent it through email. Thank you. Just if you haven't turned it in yet, just send it via email. That was for chapter 17 on epidemiology. We'll have that review activity today, so you have a folder on D2L with some material. So that will consist of concepts and then analyses. So the analyses will be independent t-test, dependent t-test, or single factor ANOVA. So I've included 4 separate analyses on the practice spreadsheet for today that we can cover, as well as some conceptual things. After exam 3 next Tuesday, we have a mini spring break on Thursday, so hope you had a chance to get out and enjoy the hopefully good weather. The 19th and 21st are work days, and I want you to take time to prepare your PowerPoint, and that will be an oral presentation. Finish up with your data collection. I want everybody to have their data collected by Thursday, April 21st. Please make arrangements to have that completed, and then for most of you, we're just talking less than 5 participants. So inferential stats are not the best option. For a pilot project, just reporting means and standard deviations is all that I'm asking for at this point. And then we have oral presentations on the 26th and 28th, and then our final exam covering chapters 11 and 17. Actually, it'll be just chapter 17 because I'll have to get in and change that. So it'll just be chapter 17 over epidemiology for your final, because we'll have chapters 9 and 11 on this next exam. So then you rate the final will be Tuesday, May 3rd from 10 to 11:50 in here. So any questions? So let me go to the home page of D2L and I can show you. So the new announcement is here, 26th and 28th. So those presenting on the 26th, Annalise, Bryant, Megan, Bree, Maisie, and Jordan. For the 28th, Shelby, Ashley, Sydney, Allie, and Danielle. For example, for the PowerPoint, I put something up on D2L for you. Your presentation should be a minimum of 10 minutes, but not longer than 15 in duration, and then be expecting questions afterwards. So you're the expert on your topic, and you need to be comfortable answering questions. So as an example, I've placed in the oral presentation folder, you have this file, and you can pull it up. And so I can quickly scroll through this, so you'll have your title on the first slide, and then you'll go into your background, and this will be great. So you'll be, when it comes time to do your thesis, and this is like kind of a trial run for your defense, so you'll do fine. And so you give a little bit of a literature review, like look in the proposal that you wrote, giving a background with key points and justification for your study and maybe where some of the gaps in the literature are at. Then you come to your purpose statement. So everybody in your proposal, remember you had a purpose statement. Your hypotheses. So you have one hypothesis, which is the null hypothesis. What's the null hypothesis? No differences, right? Between conditions or groups or treatments. The alternative hypothesis is a significant difference between groups, conditions, or treatments. So then you'll go in and explain to everyone what you did, methods, so your participants, so who was it that you tested, the stipulations, so maybe you were just requiring college athletes, or maybe it was just friends, or just a large general sample. So if you want to, you can put a table in here of your demographics, so age, height, weight, sex, year of, in this case, it was volleyball experience, so this is a thesis from about 4 years ago. Then you go into your procedures. So I didn't have you have to remember this was an actual thesis defense, so we watered it down a little bit. I didn't have you actually have them sign the informed consent, but you'll use that for your actual thesis. What the groups were, what the sessions were. So most of you, it's just one session, but some of you, maybe it was 2 or 3. So the materials and where you collected your data. So this is just a little more descriptive on what this student did. So then you'll go in and you'll describe your different conditions or protocols. So Shelby looked at the force in a squat with different footwear. So you'd go in and describe those conditions. And then for your analysis, you'll just have maybe you could put down with an actual sample that's larger what you anticipate doing with your thesis. For now, it's just means and standard deviations with just a small number of people. And then you'll present your results. So tables, graphs are good. Again, you only have a few participants, and we all know that. So this is just really just practice for your thesis coming up. So we talk about your results, and I think with a pilot study, it would be important to maybe talk about things you might change or things that you notice through the process that could be smoothed out as you go into your actual study. And then, so you'll come to your discussion and amazing. And so that might be a place where you talk about what you could do differently, the significance of the findings, the limitations or conclusions that you have. Maybe look at what are some future studies that could be done, maybe from your standpoint. And then you have your references at the very end. So is this helpful? So you'll have a PowerPoint like this, and you'll just stand up and you can borrow my clicker and just take it away. Okay, so that's what'll happen on the last week. So there two parts. So you can see the folder, Exam 3 preparation materials. Part of it is analyses, the other part is concepts. So do you have any preference what you'd like to do first? Let's jump in. Okay, well, maybe I have a copy of concepts, so maybe we can start there. Okay, so let's start here. Let's review concepts. So chapter 9 and chapter 11. Chapter 9 was on comparing differences between groups. So we went over two different types of t-tests and one type of ANOVA. And so in comparing differences between groups, we have to keep in mind that sometimes our statistical test will find a significant difference, but sometimes that significant difference can be due to chance occurrence. So when we say we have an alpha level of 0.05, what does that mean? What are we saying when we say alpha of 0.05 to reach significance? There is what percent chance of this type of error? Yep, 5% chance of a type 1 error. So that means that 5% of the time, 5 times out of 100, our statistical tests will say that there's a significant difference between groups when in reality that difference is due to chance. So there's no actual difference between groups. So 5% is not very much. So most of the time we can be confident that differences are real, but we just need to be aware that statistics are not perfect, and so sometimes differences can be due to chance occurrence. So a type 1 error is when our statistical differences are due to chance occurrence. Statistical differences due to chance occurrence. So what is a type 2 error then? I would almost rather make a type 1 error versus a type 2 error, because type 2 errors, I feel like I'm missing out on something that could be beneficial. And if I'm relying only on statistics, I could be missing out on something beneficial. So let's talk about that. So what are some other things you can use to determine whether an intervention is worthwhile? So rather than just probability, rather than just statistical probability, what's the other measure that we take? The actual magnitude of the difference. No, I'll say it, effect size, you know that, effect size, come on. So effect size is a secondary measure that we use in addition to statistical comparisons. I like effect size because any small difference, I'm willing to do that to get just to that next level. So an intervention is worthwhile if we can identify a good effect size. So a type 2 error is when there are real differences that our statistical test misses. So real differences that are missed by our statistical test. So in reality, there are real differences between treatments, conditions, or groups, even though our statistical test says not significant. Does that make sense? Okay. All right, so can we go to number 2? Okay, so coefficient of determination is sometimes used as a type of effect size. Remember how we get the coefficient of determination? We take the Pearson correlation between variables. The Pearson correlation is sometimes called the interclass correlation. And so once we have the Pearson R, or the interclass correlation, what can we do to that number to get the coefficient of determination? If you remember way back, what we did is we squared it. Yeah, we squared it. So what does the coefficient of determination mean? Well, it's the percentage of the second variable that is accounted for due to the first variable. So the percentage of the dependent variable that can be accounted for due to the independent variable. So if we're trying to predict vertical jump height from back squat max, the back squat max is the independent variable. So that's the criterion. And then the vertical jump is what we're trying to predict. So we could calculate a correlation between those two. We would have one sample of people, and we would get all of their back squat max numbers, and then we would get all of their vertical jump numbers, and then we would come up with this Pearson R that you've calculated several times, and then we would square the Pearson R, and that would give us our coefficient of determination. In other words, how much of a vertical jump is due to someone's back squat max. So the percentage of a vertical jump due to the back squat max score is the meaning of coefficient of determination. So does everyone understand how that works? Okay, all right, so let's move on to number 3. So 2 key assumptions when conducting statistical tests. So a lot of times, especially when we're trying to run projects and we're utilizing samples of convenience, we violate these assumptions, but we also like to say that statistical tests are very robust to violations of these assumptions. So the 2 of them are that your sample is drawn from a normally distributed population for the variable that you're measuring. So normally distributed population, and that people are drawn from the population at random. So as I'm looking around here and as I think about all the studies that I've done, violated that lots of times. So under ideal conditions, those 2 assumptions are in place. So normally distributed population, and people are drawn at random from the population. Okay, so let's get into t-tests. So what are the 2 types of t-tests?
Independent and dependent.
Yes, independent and dependent. So let's read question 4 together. Which type of t-test would be appropriate when 2 samples are drawn from a population? Okay, so we have a big group of people and we draw 2 samples, and let's just say that we're drawing these people at random, so we're assuming they're equivalent for the variable that we're measuring from a population and are tested on the same dependent variable but with separate treatments. Separate is the key word there. So what would be the appropriate analysis if we're talking about different groups, different treatments that are tested on the same dependent variable?
Independent.
Yes, independent is right. So how well do 2 different treatments affect your dependent variable? So independent is correct. Okay, so question number 5. Which type of t-test would be appropriate when 1 sample is drawn from a population and tested twice on the same dependent variable at baseline and post-treatment? So now you have 1 sample tested at
at the beginning and at the end on the same dependent variable. So you're comparing the same person 2 different times on the same variable. What would be your t-test? Dependent in that case, yeah. So what's another way, how does Excel give us our dependent t-test? What's the option that comes up? Sometimes called a paired t-test, because you have 2 numbers, baseline and post, and so that's a pair of numbers on the same dependent variable. Okay, so by default then, you probably can guess what number 6 is. So which type of statistical test would be appropriate if one group is tested on one dependent variable, but under 4 different conditions of the independent variable? Yeah, so single factor. So single factor means that there is one independent variable, but there can be multiple conditions of the independent variable. So for example, today we're going to look at an EMG study where we have 4 different exercises that assess the activity of the erector spinae. So the activity of the erector spinae under 4 different conditions. So the independent variable would be exercise, and then all the exercises under the independent variable would be conditions. And then assessing the same dependent variable for each of those conditions. Okay, so for which, question 7, for which type of statistical test is the F ratio used? You'll want to hang on to this table. Has anyone lost theirs? I have more. You're going to want it for the exam. You're going to need it. So if you've misplaced it, you can come up and or just raise your hand. I can hand you another. So the F ratio is a single factor ANOVA. It's actually for all 2, yeah. So it's just ANOVA. Does it a single factor, 2 factor, 3 factor. Any of the ANOVAs will use an F ratio. So if you turn over more on the F ratio, do you remember what the formula is for the F ratio? So if you look at your ANOVA table, when you get your output in Excel, it will have, on the top row, it will have the between part of the comparison, and on the second row, it will have the within part. So between conditions and within conditions. So if you're taking your assumptions to be true, and everyone that you draw from a population is in the same state, so they're all the same, so we're assuming they have the same, let's say, training status, there should be minimal variation within each condition. So minimal variation within conditions. What are we actually hoping for? We want lots of variation between those conditions. So if everyone from the population is the same, then you should put them in different conditions, and you shouldn't have a lot of variability within conditions. You should have people that are in each group and they respond in a similar way. So where you want the variation is between groups. So the F ratio is the mean squares between divided by the mean squares within. So mathematically, to get a really big F ratio, what do we want to see? If mean squares between is on top of that ratio, That's in the numerator, and mean squares within is in the denominator. How are we going to maximize that F ratio? What do we want? We want lots of variability between, so we want a very big number on the top. What about on the bottom? Yeah, smaller number on the bottom. So mean squares within, we want within groups very little variability. So that's how the F ratio is calculated. The mean squares between groups just means variability between groups in response divided by mean squares within. So how is the critical value determined in which to compare the F ratio value? Well, it has to do with the degrees of freedom associated with the between groups comparison and the within groups comparison. So between groups, you take the number of conditions minus 1. So you might have 3 conditions under an independent variable, you might have 4, and so on. You just take the number of conditions minus 1. That's the between groups degrees of freedom. So if you look at your table here, the degrees of freedom is what you find across the top. So let's say you have 5 conditions. 5 conditions under the independent variable. Which column would you go to across the top? Yeah, you'd look at 4. Okay, so the within groups comparison is n minus k. That's the total number of observations minus the number of conditions. Total number of observations minus the number of conditions. So if you have 5 conditions and you have, let's say, 8 people in your group, and each of those people is tested for those 5 conditions, 8 people times 5 conditions means how many observations? 40 observations minus the number of conditions would be what? 30. 40 observations, 5 conditions means 35. So then you'd go, so remember in the numerator we've got 4, because that's k minus 1. 5 conditions minus 1 is 4. In the denominator, we have total number of observations, that's n, minus the number of conditions, that's k. So n minus k. So 40 observations in this example, minus 5 is 35. So then you go down to, I think we've got 35 on here, and then you go across, and you come up with, 2.641, just in this example, would be your critical value. So what do we use the critical value for? So if the F ratio is greater than this critical value, what do we conclude? We say the main effect is significant. The main effect is significant. But if we've got 5 conditions, how do we know where that significance is? We don't. We just know where there's a significance somewhere, so it's the first step. So if it is significant, what's the next step? Yes, post hoc testing. So we call that follow-up testing. So question 10, if the critical value exceeds the F ratio, what is the next step in the statistical procedure? It's follow-up comparisons, post hoc comparisons to find where that significance is. So 1 versus 2, 1 versus 3, and so on. Okay, what's the post hoc procedure that we've used in this class that your author really likes? Chef. just so you know, there's a lot of different post hoc procedures. Bonferroni was the one that I always used to use for post hocs. Okay, so are there any questions on chapter 9? We'll get to the statistical analysis part here in just a little bit, but do you have any questions on concepts? So if I gave you a hypothetical scenario, would you be able to tell me what the critical value should be if I went through a hypothetical scenario? Should be able to do that. Okay. All right, so chapter 11, we just have a few questions here, 4 questions. So what is the difference between validity and reliability? Validity and reliability. Validity. Yes. Yes. So validity is, does a test measure what it is supposed to measure? Does a test measure what it is supposed to measure? So if we compare reality to a target, you want your test to hit the target right in the bullseye. So as Ashley was saying, reliability is consistency. So for a test to be valid, it has to be reliable. For a test to be valid, it has to be reliable. So can a test be reliable without being valid? Yeah. Yeah. So you can be consistently inaccurate. So we want both. Test, in order for a test to be valid, it has to be reliable, but a test can be reliable without being valid. Okay, so question 12. Which type of criterion validity would be evident when an estimate of body fat percentage via skin fold assessment correlates highly with an MRI scan to measure body fat percentage? So there's 2 different types of criterion validity. There is concurrent and predictive. So those are 2 subtypes of criterion validity. Concurrent validity. What does that word concurrent mean in a general sense? Concurrent. At the same time. So you would expect that a certain result on a skin fold assessment would be concurrent with an estimate or a measurement from an MRI scan. So concurrent validity would be the answer to question 12. So in agreement. So that's why we have convenient field tests like skin folds, is because they're more cost effective and faster versus something like an MRI. So what is the procedure called when a prediction equation formulated from one sample is tested on a different sample? So that's really the best way to see if a prediction equation is done well. After you make the equation on one sample, then you use it on a different sample with the same characteristics. So we call that cross-validation. Cross-validation. It's one of the best ways to, I guess you could say, validate your prediction equation. Would be testing it on multiple samples. So which type of correlation is used to assess the reliability and relationship between multiple measurements of the same variable? So we just did this one on a spreadsheet last time. So the interclass correlation is the Pearson correlation. So with the Pearson, we're looking at the relationship between different variables. But what if we just want to know reliability? So we're taking a sample of people and we're testing them at the beginning of a study, we're testing them multiple times on the same thing. So we want a nice stable value before we start our study. Sometimes that's hard to get when you're testing novice people because they adapt very quickly and they change very quickly, so it's hard to get a nice stable value. So what type of correlation would we use between multiple assessments of the same characteristic to demonstrate reliability? So it's not inter, it's intra-class correlation. Intra-class correlation. Okay, so do you have any questions over concepts of chapter 11? So this is a good study sheet, so I'll give you scenarios and I'll ask you to explain concepts. Okay, so those are the concepts. So before we get into our analyses, does anyone need one of these sheets? Yes. Okay. All right, so please go ahead and we can go through this together. If you're really fast and you want to just take off on your own, that's fine too, but so I've explained each analysis with an introduction here. So you can see up in the formula bar and in red here, this study examined mean repetition power output over 5 repetitions. So that's the dependent variable. 5 repetitions, taking the average over the 5 in watts. For a bench press, so that's the independent variable, and then there's 3 different conditions under the dependent variable. So, let's see. Under 3 different conditions, as follows, 50% 1 RM, fast repetitions, 50% of 1 RM bench throw, and 50% of 1 RM bench throw with prior whole body vibration. So you can visualize those 3 conditions. So we have our conditions. There are 3. So can you look at the table and tell me what our critical value is going to be? We have 10 people and 3 conditions. So how many total observations do we have? 10 times 3 is 30. So the number in the denominator is going to be what? N minus k. So 30 observations minus 3 conditions, you should be looking at 27 down the side. What's the degrees of freedom for the between groups comparison going to be? K minus 1 is 2. So we need to be going to 2 and 27. So we come up with 3.354. Everybody see where that's at? That's our critical value. That's the value that we want our F ratio to exceed to have significance. So all right, so we can place our cursor somewhere out of the way because we know there's going to be tables there. So, so you want to go to your data analysis, okay? And what am I going to select here? Yep, what type of ANOVA? Yep, single factor ANOVA, because there's one dependent variable. one independent variable. So if we have more than one independent variable, then it would be, you can do up to 2 factors with Excel. Click OK there, and then for your input, you always want to make sure that you get the label for the column as well. So the 50% of 1RM fast reps and so on. Make sure you have all 10 of observations for each condition. And then you'll want to check on the labels there for the first row. And the only other thing would be to click on output range. And you can come over to this side and you can just click somewhere where it's going to be out of the way with enough room. And so once you've done that, click OK, and you have this nice ANOVA table. So these tables are nice because if you were to do your final paper for your thesis, you could just take this table and just put it right in your results section. So looking at our table here, we compare our critical value that we already knew before the comparison with the F ratio. So again, F ratio is taking the mean squares between divided by the mean squares within. So if you took these two numbers, 2,500, that's actually 25,694, and you divided it by this number, 1,919 plus whatever the decimal is there, you'd come up with this 13.38. And so, do we have significance? Yeah. So, you can see the p-value there is pretty significant. So, how do I change a number from an exponent to just a regular number with some decimals? What do I need to do in Excel? Remember? So, what you could do, you probably want to increase the size of the column to start with, and then you can right click on it, and you go to Format Cells, and you can just click on Number as the category, and you can, we'll just start there with 10 decimal places and see what we get. So you can see that value is a lot less than 0.05, so that's another way that we know we have a significant comparison. Okay, so the real critical numbers are noted right here. So these are your average values for power with each of those three conditions. So you would want to order your averages from largest to smallest. So let me enlarge this just a little bit. So can you see here, 50% of 1RM fast reps, there was an average of 467 watts. 50% of 1RM bench throw reps, so that's 470 watts. And then your prior whole body vibration there. So these averages is what you're actually going to compare for your post hoc comparisons. So you can take each average, so 556.9 watts, and that's condition 3. So anywhere you have highlighted in yellow, that's where you'd want that number. So when I paste, what do I want to do when I paste? Because you have lots of choices. What's the one that you want? Just values, yeah, is right. So you make the second clipboard there. You could do the same because that's highlighted in yellow, okay? Okay, so then you take your second average here, copy it, and then you see the yellow highlighted area there, so then you click on that. So you want that number there. And then 556.9, so you'd copy that. Oh, wrong one, 467, excuse me. 467 is my lowest one, so I would put that right here in the condition 1. Okay, so can you see all I'm doing is just placing these cells in the right spot so that I can take the difference. So the cells highlighted in yellow, condition 3 minus condition 2. Those are the differences that you want in doing your post hocs. So we can go over to the right, and so right here. So these yellow cells is where you're taking the difference between means. So you can quickly do that. Start with an equals, just like always, and then you click on 1, and then you subtract the other. You're just coming up with these differences. So they're highlighted in yellow just to make it easier for you to, but you want to order them from largest to smallest. Condition 2 minus condition 1. Okay, not much between condition 2 and condition 1, as you can see there. Okay. All right, so remember from our textbook chapter, this is how we get the critical value for the chef comparison. So to make it easier, we're dividing the equation into 2 parts here. And then we come up with this big thick border. That's where your critical value will be for the chef test. So let's go ahead and do this together. If you haven't already done so, you can take the first half of the equation is equals, and then SQRT, take the square root. So what is k minus 1 equal to in this case? Yeah, so it's 2. And then you multiply by the F critical value, so if you want, you could just scroll over and just click on that. That's 3.3541 and so on. And then you could close your parentheses there. And you come up, how many came up with 2.590? Yeah. Okay. All right, so the second half of that equation is like this. So it's going to be another square root, so SQRT. It's 2 this time, not because it's k minus 1, it's just that's the way the equation is. It's 2. And then you want to multiply that by the mean squares within divided by the number of people that are participating. So it's going to be 10. So it's not the number of observations, it's the number of people. So you scroll over here to get your mean squares within groups. That's going to be this 1,919 and so on, divided by 10. So you scroll back over here so you can see what's in that cell, and then you close your parentheses there. Okay, so I hit return and I get 19.596. Does everybody agree? Coming up with that. Okay, so the only reason we do that is it's a lot easier to do the equation one part at a time versus all together. So in my experience. So then all you do is just multiply the first part, use your asterisk there, multiply by the second part, and so then you have your critical value. So what do I do with that? What do I do with that 50.75? What am I going to do with that now that I have it? Mm-hmm. So how do I know if something's significant? So I have my nice little critical value there. And how do I know if something is significant? The difference between means has to be bigger. So you can see the difference between condition 3 and condition 2 is 86.1, so that's greater than 50.75. So we could say that condition 3, which is your, what was that? That was your bench throw with prior whole body vibration, is significantly different versus just a bench throw, is the conclusion. So also we can say that condition 3, bench throw with prior whole body vibration, is significantly different versus bench press fast repetitions. So that was condition 1. So I can say that because this number, this difference between the average of these conditions is 89.4, which is greater than what my critical value is here. Is that, everybody, is that making sense? Nod your heads. Yes? Okay. All right, so what about condition 2 versus condition 1? So it's not. So that difference is not because it's less than what we have here, our critical value. Okay. So that wraps up the first one. Is everybody good with that one? Okay. All right, so the next two, analysis 2 and analysis 3, are pretty fast. Okay, so what happened in this study? All right, so this study examined the blood lactate response. How many of you have measured blood lactate? Yes, all of you. That's the dependent variable, blood lactate response, following a lower body circuit protocol. That's the independent variable between groups, between two groups. In group 1, each exercise set was performed to repetition failure. So what does that mean? It means you lift the weight till you can't lift it anymore, right? Okay, so that's what they did. Group 2 was each exercise set not performed to repetition failure. Okay, so that was the non-failure group. Both groups performed the same total workout repetitions due to the non-failure group performing more exercise sets to equate the total repetitions. So they performed an equal volume. The total repetitions was the same, it's just that one group did fewer sets to failure, the other group did more sets that were not to repetition failure. So you have two different groups. You have a repetition failure group and a repetition non-failure group. And so you have 10 participants in each of those groups. So separate groups means what type of t-test? Independent t-test is exactly right. So independent t-test is what we're going to do. Okay, so for this particular study, would a one-tailed or two-tailed test be most appropriate? So do we know from the outset what direction results are going to go? Do we have any idea whether one group will be different than the other group in terms of blood lactate response? They both did the same amount of work. We really don't know, so what do we select? It's going to be a two-tailed test, is right. So you would just put in this spot, you would say, I'm going to do a two-tailed So all that I'm asking you for in this case is just the p-value. So was there a significant difference in the blood lactate response between conditions? If so, what was the p-value? So we can run just a quick t-test in this case and just to come up with a p-value. So in this case, all we have to do is just equals and then just punch in t-test. Equals. Okay. So how many of you can see this little blurb right below that cell? So you have a t-test and you have array, that's one set of data. Array 2 is a second set of data. Tails is going to be 2, and then you'll be given a choice of type. So we want independent t-test. So for array 1, all you have to do is just don't highlight the label in this case, you just highlight the numbers. And then you put comma. And then you'll highlight the second array and comma. And then you can see it gives you choices, one-tailed or two-tailed, 2. So just put 2, comma. So you can see everything that you're doing in that cell, you can see right up here. You can see what's going on in your test. So there aren't very many cases where we say unequal variance. So almost 100% of the time you would just go equal variance. So 2 samples is just another way of saying an independent t-test, 2 different samples. So then you would just put 2 and close your parentheses, and then you can click return there. So was the difference significant? Yeah, yep, it was. How do you know? Yes, very good. Less than 0.05 is exactly right. So if we wanted more output with our results, or if we were curious about means, we could just quickly, do the average for each one and just kind of see. So the average on that one was repetition failure is 14.67. So I'm just taking averages here, just to see, because I couldn't remember which one was higher. So performing the sets to repetition failure produced a blood lactate of 14.67 millimoles per liter. Remember those little yellow units that you have in the lab that you, Annalise, have you had the pleasure of pricking your finger yet, getting some blood lactate? So 14.67 millimoles per liter is the blood lactate. So you can see then, despite doing the same amount of work, the same total repetitions, the non-failure was at 9.48 on their blood lactate. So that was significantly different. Okay, all right, so does everybody understand that one? Okay, so we got 2 more to go. This is another quick one. Okay, so looking at the failure group separately, so the repetition failure group separately, looking at how much work they did at a given amount of weight for each exercise combined at the pre-test versus the post-test. So from biomechanics, what are the units we use for work? Joules is right, yeah. Okay, joules of work. So how do we calculate work? The amount of load multiplied by what? Yeah, how far you move it. So for this particular study, we used motion capture. So I had one person filming every single exercise, and then we put the video into the motion capture software, and we were able to actually measure the distance of every repetition, how far vertically the weight was moved every time. So that's how we came up with work in joules. So essentially what you've got is the work at the pre-test, the work at the post-test. Let's go ahead and do these calculations. So you go ahead and take it from here. So the mean of your pre-test, the mean of your post-test, standard deviation of your pre-test, because we're going to do effect size. So just take the average of the column there. For the pre, take the average of the post. So for standard deviation, what do I need to type in? Equals dot S. Why dot S? It's a sample. Exactly right. Okay, so one tail or two tail? One, why would you say that? Other than that, even though I agree that's a very good point.
You're doing the same test.
Yes, and so what would you expect? You'd expect them to do better on the post-test. Second time through, you would expect it to be larger. So in this case, it would be a one-tail test. Okay, so what type of t-test though? So you have 10 people that were tested on the same protocol twice. Pre-post is, just take Brian's logic. What was the last spreadsheet that we did? It was independent, so this one must be dependent. So in other words, what's the other word for dependent? Paired is right. So you have the same person tested twice on the same variable. Pre and post is a dependent t-test. So come up with a p-value there. Looks like I didn't put it. I should have put a square in for the p-value. I missed that. What are you coming up with for your p-value, by the way? 0.025. Everybody agree? P-value 0.025. So equals t-test, right? So then you just highlight your first array, comma, highlight your second array, comma, and then it's going to be a one-tail this time because we're expecting an improvement, and then it's going to be a paired. So it's going to be another one, like that. So, yeah, so significant? Yes, less than 0.05, okay. So can you calculate effect size for me? What's the formula for effect size? The post-test mean minus the pre-test mean divided by the pre-test standard deviation. So that's why we calculated these means up here to begin with, is you need the post-test mean, whatever you got in this cell, so you've already done it, minus the pre-test mean, divided by the pre-test standard deviation, which you already calculated in this cell. So what are you getting there for effect size? What do we got? So was the magnitude of the effect size for total work based on the scale proposed by Ray, so you've seen this several times, if the sample was recreationally trained. What was the magnitude of the effect size? Was it trivial, small, moderate, or large? Moderate. Okay, so what'd you get, Sydney? 1.09. So for recreationally trained, that would fit right here. So Sydney is correct. That would be moderate. Did everybody get 1.09 for effect size? Post-test mean minus pre-test mean divided by pre-test standard deviation, and then say, okay, well, what was the sample? And then you look at the effect size, and you can say, okay, so that's a moderate effect. So I like effect size better than I like probability, because the effect size is real, probability can be a little sketchy. Okay, so we are now on the last one, gang. So we're almost done, so just hang with me just a little bit longer.
Wait, Jeff, can we go back to the effect size?
Yeah.
We get 58,000.
Yeah.
That's what I got.
All right. So post-test mean minus,
Also just,
did it work?
Oh, yeah, you got it.
Okay, so 1.09 is,
0.8.
okay. Okay. All right, so very last one. Now, on the exam, I'm going to give you one that's more than three conditions. So be prepared. This is to prepare you for that. So this study examined EMG activity of the erector spinae. Okay, so that's the dependent variable during different lifts. So the lifts are the independent variable under 4 different conditions. So each exercise represents a condition. So barbell overhead press, barbell bicep curl, barbell back squat, barbell deadlift. So 4 conditions under the independent variable. So let's just go ahead and let's identify, see if you can identify what the F ratio will be. So we have 10 people that did 4 different conditions. So the between, what is the degrees of freedom for the between conditions comparison? 3. Why would you say that? Because, yes, so K minus 1 is 3 in this case because there's 4 conditions. So K minus 1 is 3, so we're going to go to a column that has the number 3 above it. Okay, so 4 conditions, 10 people. How many total observations do we have? 40. So what is the degrees of freedom for the within conditions comparison? Yes. Why would you say that? Because 40 observations minus 4 conditions is 36. So we're going to go down to 36. And we go across. Yep, 2.866. So our F ratio has to be bigger than that for, we say the main effect is significant. If the main effect is significant, then we go into secondary comparisons. Okay. All right, so this is your table here with the means. You want to try to,
single factor normal limit.
yes, because there's how many independent variables? 1. That's a single factor. So there can be multiple conditions under that single factor. So let's just go ahead and got your data analysis, and it's going to be single factor. And we can see, may need to re-highlight here. So make sure we have everything. Really important that you make sure you get everything included, the labels, as well as all of the observations. So click labels, output range, let's put it
we're right there. And then we're here, so. Okay. So the average activity of the erector spinae went like this. So the lowest was the barbell overhead press for the erector spinae. Second was the barbell bicep curl for the erector spinae. Third was the barbell back squat. And then the highest was the barbell deadlift. So these are your averages. So those are the numbers you want to place down in your table. So tell me, was the main effect significant? Yes, how can you tell? That's a pretty big F ratio. That means we have lots of difference between conditions and very little difference within conditions. So the F critical, we already identified that, but it's a lot smaller than this big F ratio here, so. So go ahead and move your averages where they go. So 16.118, put that in the overhead press column. It's gonna go there, and there, and then you've got 31.716. So that's gonna go these three right here, there. 57.306. That's under the back squat, so you're going to just put it just where the highlighted cells are. And 68.185, copy it, and we'll just, so all I'm doing is just putting my means in place so I can get ready to calculate differences. So all those means are in place now. So I'm taking the difference between deadlift and back squat, deadlift and bicep curl, deadlift and overhead press, back squat, bicep curl, back squat, overhead press, bicep curl, overhead press. So can you see how I'm just going progressively through taking differences between each one? That minus, it helps when the cells are highlighted, doesn't it? You can kind of navigate easier. So deadlift and overhead press. So then 3 to go. Squat and bicep curl, squat and overhead press. All right, 1 to go. Okay. So how many of you have got this far with these means in this cell? Okay. So now all that we have to do is get that second critical value and then compare it with your differences. And so that's relatively easy, so start in on that. So it's just repetition. Statistics is a lot easier if you use
use repetition. So K minus 1 again, what did Shelby say earlier? Not 2 anymore, it's 3, because we have 4 conditions. So you're going to put square root, open parentheses, 3 times, and you'll just scroll over here to your table to get your critical value, which is 2.866, and so on. Close your parentheses there. So how many got 2.932 for the first half there? Okay, so second half, SQRT, it's going to be 2 because that's the equation, not B because of anything with the conditions, times mean squares within. So you can just go over to your table here and click on that 175.45 divided by, it's going to be the number of participants that you have. So in this case, we have 10 participants. Close your parentheses. 5.924. Everybody consistent? So then you'd just multiply those two together. And so 17.37. So what do I do with that? Shrink it down a little bit. Okay. So what am I looking at here? Once I have this number, what do I look at? Compare it to over here. So deadlift versus back squat, significant? No. Deadlift versus bicep curl, significant? Yes. Deadlift versus overhead press, significant? Yes. Back squat versus bicep curl, significant? Back squat overhead press? Yep. Bicep curl overhead press. No, that's the one that is not, along with the first one. So between deadlift and back squat, the erector spinae activity was not significantly different, albeit it was higher during the deadlift. The bicep curl versus overhead press, again, that was less than our critical values, so the difference in the erector spinae would not be significant there as well. Okay, so questions, concepts, analyses, independent t-test, dependent. Okay, so make sure you save your work from today because you'll need it for the final, or not the final, but for the exam on Tuesday. Okay? All right, have a good weekend. Thank you.